are honored to have Vladimir Koylazov here.
Perfect.
With Chaos Software. And once again, I just want to make one announcement, actually two announcements. One is hopefully all of you have been scanned because your badges are your entry into the daily raffle for the HP Dream Color display. So hopefully, if you haven't been scadged, we have a couple people running around with scanners. Also, I wanted to remind you that all of our presentations are being recorded. They will be available at the end of the day. I'll be posting them. So if you want to tell your friends and your colleagues to check out anything that you saw here in the theater, go to nvidia.com/SIGGRAPH 2013, and you'll see them all there. With that, I hand it over to Vladimir.
Hi. Can you hear me? I guess yes. All right. So I'll start with a few words about what I'm going to talk about today. Chaos Software writes mostly a renderer called V-Ray. We have it integrated in various modeling applications like 3ds Max, Maya, Softimage, Rhino, SketchUp, and so on. And it's traditionally been a CPU renderer, but in the last few years we also have a GPU support. So we have developed a new system, V-Ray-RT, for interactive ray tracing, and it runs on Nvidia GPUs very well. So I'm going to give you a little more details about how the whole thing is organized. So I'll start with a short demonstration of V-Ray-RT in 3ds Max. So this is the regular 3ds Max viewport. We have a relatively simple interior scene. I've got V-Ray-RT set up as active shade render in 3ds Max. So if I go and start this, it will take a while to load the scene, but after that I get a very quick preview of how my final scene is going to look like. And once you get to this point, you can start changing pretty much anything in the scene, and V-Ray will take care of updating the final image. So if I want to change the curtains here, for example, remove the checker pattern, I can do that and I can see the result right away. Or if I want to change the color of any of the furniture, I can do that and I'll see the results almost immediately. So this is a very handy way to set up complicated scenes and to figure out the correct lighting or the correct materials. And NVIDIA GPUs have helped us a lot to get to this level of interactive performance. Let's check out another scene in Maya. In Maya, V-Ray-RT is again an interactive renderer, and let's see. We've selected the CUDA engine here. So what I have set up here is render elements, and I'm going to talk about this in my presentation. But we have the ability to. So this is the final scene, but we also have the ability to extract different lighting components from it. So if you want to check out the contribution of just a single light in the scene, it's very easy to do that right inside of the V-Ray frame buffer. And you can also change any materials, move the camera around and so on. It's very easy and it's very interactive. All right. So this was just to give you an idea of what V-Ray-RT actually is. And let's go a little bit behind the scenes. So the goal with V-Ray-RT on GPU was to allow users faster interactions and to speed up the look development for a scene. Like what you saw, you can basically take a scene and move lights around and adjust the camera point, anything, and you get almost immediately a final view of what the rendering is going to look like. But beyond that, we also want to be able to use V-Ray-RT to render final render. So it's not like a preview render only. You want to be able to take it and do your final image with V-Ray-RT on the GPU. So it had to support a lot of stuff that you normally find in production renderers, So we've had to support things like motion blur and render elements and various non-physical features that people need in actual productions, like being able to hide objects from reflections, refractions, or making lights invisible, and so on. We also wanted to use distributed rendering because when you have a heavy scene, so one machine is usually not enough to get good interactive performance. So you can actually get several machines and plug a good GPU in them, and V-Ray-RT will be able to use all of those machines to render one single frame. And this increases the interactive performance quite a bit. And of course, we wanted the whole thing to be very responsive, so that you can get the result immediately after you change anything in the scene. You should be able to see the result. This is what the overall structure of V-Ray-RT GPU. On the one hand, we have the client machine, which is on the left side, which is the machine where the user is running the 3D application, like 3ds Max or Maya, with V-Ray installed. And we have the V-Ray part that the users see and they can adjust. And then there is the V-Ray renderer running in the background. This is command line window that you saw maybe popping around here, which is doing the actual rendering. And it is talking to any other machines in the network that you may be using. In this case, I don't have other machines. All the rendering is done on this machine over here. But if you had more machines, then they could be used. And the whole communication goes over a standard TCP/IP connection, so it can even go through the internet. It's a bit slow, but it works. So a little bit more details about the render client. So its main goal is to handle all the user interaction. So when the user changes something in the scene, moves lights, cameras, or changes materials, the client machine, the V-Ray portion on the client machine has to capture that and translate it into V-Ray specific commands that it needs to send over to the render server so that they can actually compute the image. And once the results get back, the client machine has to display the V-Ray frame buffer. Like in the case of 3ds Max, this is the active shade window that pops up, and in the case of Maya, this is the V-Ray frame buffer. So this is basically all done on the client machine. And it's not necessary for the client machine to actually take part in the rendering. So if you have a very weak machine that doesn't have any GPUs, but then you maybe have another workstation that has a powerful GPU, you can use that to do the actual rendering, but you can display the result on your own workstation, even if it doesn't have a GPU itself. So that's very cool. Or you may have one machine with a few GPUs plugged in there that you can share in the office and have different people use that. It can be very handy. The render server, on the other hand, is the portion of V-Ray that does the actual rendering. So it has to get the initial scene. So when you press the active shade rendering max or the IPR button in Maya, there's a little translation phase that needs to happen so that V-Ray takes the scene and transforms into its own format, and then it needs to send this to the render servers. So this usually takes a little bit of a while. But after that, whenever the user makes any changes to the scene, we just send those changes. The render server applies them to its local copy of the scene so that it always has up-to-date view of the scene. It computes any data that is required from it, and it gives back the results to the V-Ray client machine. The smallest unit of work that the render server can handle is an image sample. So we don't pass individual rays for tracing between the machines. It's just whole image samples. These are uploaded on the GPU. The GPU does all the ray tracing and the path tracing, computes some colors back, and gives them to the render client machine, which then assembles the final image and shows it to the user. And if you have distributed rendering or if you have multiple GPUs, then different machines will work on different parts of the image, or different GPUs will handle different parts of the image. And one of the problems that we had was how to keep the GPU busy as much as possible, because there is the display phase, which needs to happen on the CPU, like the final frame buffer that the users see. This is assembled on the CPU. All the scene interaction happens on the CPU as well, but we want to be able to use the GPU for rendering, and we have to keep the GPU busy for as long as possible. So we don't want to have something like here on the left. You can see a traditional application where you have some work to do on the CPU to prepare the data for the GPU, then the GPU does some calculations, you get the results back on the CPU, and then the whole thing repeats. But you can see that on the left side of the image, the GPU is not busy the whole time, like there are gaps. And this is not good, because we're wasting the GPU's time. So we had to figure out ways around this, and the way we did this was to use multi-threading. So we have several different threads, and each of them is using a different CUDA stream to prepare work for the GPU. And also some tasks like uploading data to the GPU and getting results back can also be performed in parallel with other tasks like calculations on the GPU. So the connection between the render client and the render server is a bit more complicated, so it doesn't go just like through a single place, but actually we have multiple threads running on the render server, and each thread completely separately communicates with the render client machine, requests data for calculation, does its own thing, and then gives the result back to the client machine. And then all the threads might be using the same GPU, or they might be using different GPUs if you have several GPUs on the system. But what that allows us to do is to go to the right side of the picture, and you can see that in this case I've made the chart with 3 CPU threads. So each CPU thread separately from the others prepares some work for the GPU, and then gives it to the GPU one after another. So we can get completely we can maximize the work the work the GPU does. So before we did that, the GPU was like maybe only full at 50% or so, but when we added multi-threading, we managed to keep the GPU busy for like 99% of the time, which is very cool. And it also goes for multiple GPUs, so it's a system that allows us to use the GPUs very, very efficiently. The algorithm behind V-Ray-RT is unbiased path tracing. Basically, we didn't want to do any radius caching or light caching or any other algorithms that we have in the production V-Ray. And we didn't do it not because we couldn't do it, but because we didn't see much point in that, because the GPUs are so much faster than the CPUs that it just didn't seem to be a useful thing to do. Like all the biased methods like irradiance maps and light cache, we developed them because the machines, the CPUs were too slow back then, so you couldn't really get a useful image with just brute force path tracing, even though it's the most accurate algorithm that we would like to use eventually. But with the GPUs we could do that, so we decided that we could just skip the whole biased part and completely focus on unbiased path tracing. The ray tracing is still adaptive, so we try to put more samples into parts of the image that actually need it. So if you have like a flat wall with constant color, we won't really spend a lot of time on it. And that particular part of the calculation is handled on the CPU. It analyzes the image and figures out what's the noise level so that it can focus the GPU on just the right parts of the image. And we're also working on some other algorithms to improve effects like caustics, which may be really hard to render with the brute force method. For the actual ray tracing, the intersection of rays with triangles in the scene, with the scene geometry, we have a few different acceleration structures on the GPU. They're all built on the CPU, but we upload the structures on the GPU afterwards. For regular non-instance geometry, regular triangle meshes, we just use a binary KD tree. And it's the exact same KD tree that we have in the CPU version of V-Ray, like in the full production V-Ray. We experimented. I know there was at some point a lot of research into optimal ray tracing structures for GPUs and so on. And we did look into that, but in the end, we just chose our original structure that we had before on the CPU, and it worked just fine. And when we compare it to other methods, it works just as well. We also have another KD tree for motion blur geometry. So we don't do sort of like other renderers do motion blur by doing multipass rendering, where you can see the image, the geometry moving one step at a time to get motion blur. We don't do that. We do actual 3D motion blur right on the GPU. So we have a separate motion blur KD tree for that. And we also handle instancing, and for that we have yet another ray tracing structure. It's a BVH, and then for each instance it has its own KD tree. And here is actually an image done with the instancing structure, which is this is done with a plugin for 3ds Max called Forest Pro, which is a very simple to use plugin for doing massive scattering of geometry, and in this case it's just one tree scattered many times. It renders, so this particular image rendered in like 15 seconds. Beyond geometry, you also need to be able to handle different lights and different materials. For the lights on the GPU, we support a fixed type of light sources, which will pretty much cover everything that you might normally need from a renderer, like point lights, directional area lights, mesh lights as well, and of course dome lights for image-based lighting. So you can get a nice HDR shot with a spherical camera, and you can light your model very easily. And I'm going to show this a bit later on. For the materials, we support a layered BSDF model, which can represent most of the materials that people normally need. We support a couple of different BRDF models for glossy reflections, which we have also in the production V-Ray, like Fong, Blin, and Word BRDFs. People can layer all these separate BRDFs to create complex materials like carpent shaders. Works pretty well. And we're also working right now on supporting subsurface scattering and volumetric effects. So this is an image that was done with V-Ray RTGPU in Maya, and it has a more complicated carpent shader, which is composed of 3 layers. There is a diffuse layer, a glossy layer, and then there's a clear coat layer. For textures, the problem that we had is that textures can be very complex. For even simple scenes, people like to do it. Of course, they're always bitmaps, but people want to do color corrections to them, and blend between different bitmaps, or use procedural textures. In C++, this is very easy to do for the production V-Ray, but for the GPU, it's not so easy because we don't have virtual functions. Originally, we didn't have virtual functions in CUDA. We do now, but the performance is not quite what we would want. And because for whatever reason originally we wanted to do the whole thing in OpenCL, we couldn't use those virtual functions because they were not available. So what we did instead is we developed a very simple high-level virtual machine that interprets the texture shaders on the GPU. So we take a complex texture tree like the one on the, well, this is a simple one really, but to render something like this on the GPU, we generate a sequence of instructions for each of the individual nodes, and then we put this structure, this sequence of instructions on the GPU, which then interprets them. Each V-Ray texture plugin provides its own texture instructions, which are put together into one shader. And to make things as efficient as possible, because bitmap textures are the ones that are most often used, we made a bitmap read one single virtual instruction. But other textures like color corrections and mix maps and so on are a few more instructions. And finally, beyond all the lights and materials and the ray tracing, we need to be able to handle render output, and we wanted to add support for multiple render elements, because beyond the beauty image, beyond the final picture, people want additional things like z-depth, normals, multi-matte render elements for extracting masks, They also want to be able to split an image into multiple lighting components, like they want to have the GI separate or the direct illumination separate. They want to be able to split out the reflections, refractions, the diffuse lighting. So we had to work on all of that, and it works in the same path. So we don't re-render the whole image multiple times to get that. We just extract this information right from the same rendering process. And because of the way the whole system is coded, we don't store the final image buffers on the GPU, so we can actually render very, very large resolutions. Here is an example of the car model that I showed earlier, but this one is split into some different render channels. So we have the first image in the top left is the final image, but then we have the diffuse filter color, then we have the global illumination, here is the direct illumination, the normals, and finally the reflection. So, as a few final words before I show you some more stuff in 3ds Max and Maya, we see GPU rendering is becoming more and more widely adopted, and there are several reasons for that. One of them is that CPU speeds have pretty much come to a halt in recent years. Like, CPUs are not really getting any faster. You get more cores, but there's a limit to that. Like, you can't fit an arbitrary number of cores in a machine. But on the other hand, GPUs are getting faster and faster all the time, so that's good. And initially, a big problem with the GPU was that they had very limited memory, but we see this improving a bit. So Nvidia released a 6 GB card earlier this year. There'll be even bigger cards probably sometime in the future. So memory is probably not a big problem anymore. Like, even 6 GB is a lot of memory, and you can fit a lot of geometry and textures on them. And if I compare this to my first workstation, which has like 512 megabytes of system memory, that was like, that's still a lot, and people still work with that. So GPUs are improving in that regard, and they're getting more and more programmable. Before around the time we started looking at GPUs, they were just at a point where you can do very interesting and complicated stuff, but you couldn't really take a whole just your normal C++ code and plop it on the GPU and expect that it will run. This is still not quite the case, but things are improving, and we can do more and more stuff on the GPU, and it's getting closer to the production CPU renderers. So we believe that GPU rendering is here to stay, and it's only going to get better with time. All right. Let's show you. Okay. So we only have 5 more minutes left. So, do you have any questions? No?
Actually, we have a question from our virtual streaming community. So
All right.
let me read that to you. What kind of performance gain can I expect by adding additional GPUs to my V-Ray RT render system?
It's pretty much linear. So if you add if they're the same GPUs, right? If you add a second GPU, it's going to be twice as fast. If you add 2 more, it's going to be 4 times as fast, and so on. It's pretty much linear.
Okay. All right. Well, our viewer, I'm sure, appreciates that answer. Do we have any questions here in the theater?
What's the ATA for the motion blur and full quality production?
I'm sorry, can you repeat that?
What's the ATA for the full motion blur and quality production of the real?
Oh, we already do motion blur. Like the latest visual versions of V-Ray already support motion blur. And render elements are not yet released, but we're the next major version of V-Ray, which is V-Ray 3.0, is coming out later this year, and it has support for render elements. So that's coming.
Can you mix different Quadro cards and GeForce cards together using RT?
V-Ray doesn't care, but it depends on the drivers. We found that sometimes there are issues when you mix cards with different architecture. Usually it works, but you have to try it. Like.
Any other questions for Vladimir? up. Yes?
Hi there. So you talked earlier about the KD trees.
Yep.
Are you calculating those on the CPU and then just transferring them over
Yep.
to the GPU?
Yep.
Yeah. Have you experimented at all with building them on the GPU, or they're just good enough on the CPU?
I'm sure we'll get to that point, but there are more important stuff to work on first.
All right. Well, if there are no more questions here in the theater, I want to say thank you again to Vladimir for joining us.
Thank you all for coming.
All right, next coming to the theater in 10 minutes is going to be a presentation on augmented reality. You don't want to miss it. It's with Matteo. So we'll be back in about 10 minutes with that. Hope to see you then.